Hello everyone, hope you're doing fine. I want to thank the previous speakers for their enlightening talks. Let's begin. The topic of this keynote is how to get started with applying deep learning to computer vision. Along the way, we'll talk about some of the key challenges that a developer faces. We'll take a look at an open source toolkit called MonkAI, which claims to ease the lives of developers. We also have a hands-on coding session around building an image classification model, and a little brief about some core application areas of MonkAI and object detection, and furthermore. Before we begin, I would like to introduce you to who we are. Me and my co-speaker today, Abhishek, are the co-founders at Tessellate Imaging. We help businesses and startups across the globe set up their computer vision infrastructure. So we deal with design, development, and deployment of computer vision applications at scale. In fact, we've been doing this for the past 7 years now across a broad spectrum of imaging modalities. If you look at the history of computer vision research, image processing and artificial visual perception has been around since storage and transmission of digital images became a necessity. From compression, enhancement, to automating object localization and tracking, researchers have come a long way. And we are now seeing real-life applications of AI, which were science fiction just a few years back. Applications of CNNs have seen a tremendous rise in their applicability to computer vision. This is a chronological scale of progression of neural network research. This shows a tremendous gain being made over the past few decades. If you look at the amalgamation of computer vision, especially applying deep learning to computer vision, you come across these broad components. So you start out with a large visual data set. This could be labeled or unlabeled depending on your purpose. On the algorithm front, you have two. First, you have a training algorithm, which is like teaching an artificial brain a new concept or maybe trying to further upon an existing knowledge base. The second is inference, where we take a trained artificial brain and ask what it sees in a visual signal. Optimizations and speeding up of both accuracy and efficiency for these algorithms are an open-ended research problem, and teams across the globe are trying to pursue this goal. One of the few contributing factors to the sudden rise in applicability of deep neural networks is the availability of fast compute power. Of course, even this is getting faster and better as embedded engineers design and develop faster and better processors. For example, the latest advent of TPUs. Despite having years of expertise in software engineering, many a times organizations fail to truly tap into the power of deep learning. Some struggle in getting the right talent, which is scarce, while others are just stuck at understanding the requirements and translating them to engineering plans. This is inevitable though, given the non-standardized development workflows for building deep learning algorithms and applications today. With multiple possible heuristics to solve any given problem, it is really a hassle to figure out a good way to do something. Our experience working on different projects over the better half of last decade has given us a chance to work closely with some of the key challenges and bottlenecks of this domain. At Tessellate, we've created processes and tools to overcome some of these challenges, like effort estimation, glue code development, dependency management, and we keep refining these with our learnings on every project. Along the way, what we realized was that some of the most widely available and popular deep learning frameworks miss out on some key software development experience. So we set out on building our own version of deep learning framework. Of course, never really trying to reinvent the wheel, but building upon the giants such as Pytorch, TensorFlow, Keras, Mxnet. These popular frameworks usually miss out on three key points, which is something that we at MonkAI are trying to achieve. What we want to do is design end-to-end workflows focused on application development while reducing the cognitive load that a developer faces in understanding the workflows. While building a deep learning application, a pathway or a template to build a particular application is usually helpful, and MonkAI tries to provide default recommendations and pathways to do that. We progressively developed a set of useful tools that now have taken the shape of our open source library called MonkAI. A library is a unified wrapper across Pytorch, Mxnet, Keras, and TensorFlow, which means it has its own low-code syntax, which is simple and repetitive. Our toolkit provides the capability to create custom models while being able to switch between frameworks. I'll hand over the presentation to our CTO Abhishek, who is also the team lead at MonkAI, to elaborate further around how a developer can build an image classification model.
Thank you, Akash, for the introduction. In this part, I'll mention a few details on MonkAI Toolkit and how you as a developer or a researcher could benefit from this open source library. So there are three libraries in this set. One is for image classification. The second one, the Monk object detection, is for object detection, image segmentation, pose estimation, object tracking, object re-identification, and activity recognition. And the third one, Monk Studio, is a graphical user interface for non-coders. Image classification is a problem where you attach a label to an object in an image. It could be a single label one like telling an image is of a cat or a dog, or a multi-label classifier where you attach multiple labels to a single image. Now to accomplish this task, there are many deep learning libraries like TensorFlow, Keras, Pytorch, Chainer, Parallel, etc. So each of these libraries have their own syntax, and the way you code in, say in TensorFlow, cannot be replicated with Pytorch using the same code or the same pattern. And every library has its own benefit. Sometimes you tend to use TensorFlow, that could be better for your data, or sometimes you tend to go for Pytorch. Hence, you have to learn multiple syntaxes. Now, when you are approaching a problem statement, you try out different methods, procedures, algorithms, and say, let's call these different attempts as experiments. So no library gives you a proper way to keep a track of all these experiments, except to some extent in TensorFlow. So TensorFlow provides you a way to visualize the training process, but does not manage everything. Hence, you lack a project management system when it comes to, say, competitions or even delivering a project to your client, which is quite essential. Also, when you start with a problem statement or a challenge in a competition, it's difficult to sometimes actually know from where you have to start and where you actually begin to prototype your experiments. For this reason, we created Monk Image Classification Library. Now, this library acts as a wrapper over all your major deep learning frameworks. To put it very simply, you learn one syntax and write codes in fixed structured pattern for all your frameworks. Now, be it TensorFlow or Pytorch, you write the same code. It also provides you a way to log and monitor all your experiments. Now, suppose you are trying to attempt a Kaggle competition. You tend to run hundreds of experiments and you want to know which one worked the best for you on the training and the validation data sets. So with Monk, you can compare all these hundreds of experiments with a single line of code. Now we also provide a notebook zoo. So it's like more than hundreds of tutorials are present in that notebook zoo, where you can learn and understand deep learning as well as computer vision. Also, it gives you a complete idea of how to use this library to its maximum potential. Now, those of you who are familiar with deep learning would know about hyperparameters. Now, these hyperparameters are nothing but knobs which you control to make your network train in the most efficient manner. Now, Monk provides you a way to reach towards these best hyperparameters using just few lines of code. We'll see all these things in detail. Let's check the library first. This is the Monk Image Classification Library. It is available with Apache 2.0 license, the open source license. Now the library is built to serve the purpose that everyone, say students, researchers, developers, as well as competition participants benefit from it. The installation part is quite simple. You install it using a single line command of pip, and based on which CUDA version that you have in your system. It can also be installed on Colab and Kaggle in a similar manner. Now it supports two modes. One is the quick mode, which is for beginners or someone looking for a faster prototyping. And the second is an advanced mode where every parameter can be changed. So quick mode is when you are trying to attempt a competition in the early days, and update mode is when you try to attempt it in a more mature way. So quick mode is a three-step process for training. Very simple. You create a project and you load an experiment in it. Now a project is something you can say as a master directory to store all your experiments over a data. So you tend to run multiple experiments on the data that has been given to you. The second step is to set up all the parameters, and we use a default function here so that every parameter is set automatically, except the data set, the model, and the number of epochs you want to train it for. And the third process is very simple, the third step, which is to train it. Coming to inference. Inference is a two-step process. You load the experiment, the one which you have initiated for training, and then you infer it on your sample image. Now, as I was talking about creating multiple experiments, you want to know which one is better as compared to the previous ones. So you add all your experiments to a comparison class, and it will create a module around it, and then you generate statistics which will give you loads of graphs on training and say validation accuracies, validation and training losses, GPU usage statistics, then the training time that was taken for each experiment, and things like those. We'll see how it works in detail. Now, for you to understand this library, we have created a set of study roadmaps, which we keep continuously updating and adding more tutorials to it. The first is a getting started roadmap, which is like a basic tutorial for you to understand Monk and get to know its every feature. A feature being like how to train or infer using Monk, what kind of data is accepted in the training engine, how to change the parameters, how to use the hyperparameter analyzer, to find the best hyperparameters, then how to create your own network from scratch, suppose you don't want to use transfer learning, and how to visualize the trained features once the training is complete, etc. Now, it's a complete set of 40 notebooks for you to get started and understand the complete library. The second one, which we are at present developing, is a roadmap for you to understand image processing basics, deep learning basics, and the advanced parts in deep learning like ResNet blocks, then how pruning of network can be done, things like those. So this part is still in development, but you can still check out the image processing basics part, which is quite interesting, a set of 9 notebooks, interactive 9 notebooks. So next is a complete tutorial on transfer learning and image classification. So every notebook here mentions the effect of changing different parameters like learning rates, batch sizes, optimizers, then losses, and what effect it has on training. And the last one here is an image classification zoo that we have created on different data sets. These data sets have been taken from different domains such as medical imaging, ADAS, autonomous vehicles, agriculture, wildlife, retail, satellite imaging, healthcare, medical imaging, things like those. And we have created a classifier on top of it. So the notebook contains 3 parts. One is how to download the data set, then how to train it, how to infer it, how to infer on the trained model, as well as we provide you a set of trained models for you to check on your own images without having to train it from scratch. We'll check one example in the end on this. Suppose that we come to object detection space. So we have seen image classification till now. Moving on to object detection. So when it comes to object detection, instead of having multiple libraries to choose from, there exist multiple algorithms like some mentioned here: YOLO, SSD, faster RCNN, EfficientNet, CornerNet, RFBNet, and many more like this. So every algorithm has its own variants. Like SSD in itself has variants, like when it is combined with ResNet, it's a different algorithm. It can be combined with ResNext models, then MobileNet models, etc. And even a single variant, say a MobileNet SSD, So researchers tend to re-implement the work in different libraries in their own styles. So it gets really overwhelming to know which variant of an algorithm to use for your work. Now, suppose you have selected a few. Trying to set up and install these algorithms in your local machine or your cloud engine usually results in new set of errors and issues that are not mentioned in the library in itself. So it takes a lot of time to set up these libraries. Now, somehow, if you have successfully installed one of them, you are now required to change the code structure so that it can take in your data set in a way that you can use it for your own purpose. Now, these research implementations come up with a pre-built input for, say, very famous data sets like COCO and Pascal VOC. So it becomes a huge task in itself to understand the codes and modify it as per your needs. Now, once a model is trained, it has to be deployed over, say, cloud or an edge device. You cannot, just a model in itself has no value. So this requires a knowledge of cloud systems or the edge systems, as well as libraries such as ONNX, TensorRT, TF-Lite, etc. So to overcome all these difficult tasks, you may call it, or issues, you may call it, we have developed Monk Object Detection Library. So it serves a low-code wrapper over all these different algorithms. Plus, every pipeline, say it is SSD or say it is YOLO, can be installed using a single step when it comes to Monk. Now, every pipeline follows a structured process with a low-code syntax, which makes it easier to train it on your own dataset. Now, at present, this library supports object detection and image segmentation, and a few algorithms for face detection. Soon support will be added for pose estimation and activity recognition, object tracking, etc. So it's a developing library, as you can see. Let's check out the library. Even though I call it a developing library, it has matured a lot over a period of 8 to 9 months now. And as you can see here, it has more than 15 different pipelines for object detection itself, and each pipeline has more than 1 to 3 models where you can actually try out and check which model would suit the best for you. Like a TensorFlow object detection 1.0 pipeline has around 22 model variants, from FasterR, CNNs to RetinaNets, etc. So all these are installable and can be set up using a single line of code, and the training and inferencing part remains the same for every pipeline. Now, every of these pipelines have a dedicated tutorials. Suppose we check Object Detection API 1, where you will get Jupyter Notebook tutorials, and each Jupyter Notebook tutorial helps you to convert your data from one type to the required type, and how to train and infer the dataset on your custom datasets. And like we have an application zoo for classification library, we also have a similar one for detection library. Now, applications of these object detection models zoo range over a lot of domains, like again, like medical imaging, agriculture, satellite imaging, wildlife, underwater imagery, ADAS. So it's a set of a complete model zoo that we keep adding on. Our contributors keep adding tutorials to it, which in itself is a good addition to this library. The third library which comes with this set is a Monk Studio, a graphical user interface over the other two libraries. And so this library is being designed with the goal that even non-coders can begin with deep learning and computer vision. So a small demo of the object detection library as well as this Monk GUI will be showcased by Akash. Before that, we'll check up a few examples from image classification library. So I have already installed the Monk image classification library in the Colab engine. Make sure you have a runtime of a GPU. You can change that using this. It has already been set to GPU. Now, the first step is the library installation, and based on the OS or the system that you're working on, you can install it using pip. Next is importing the backend library. So at the very beginning itself, you select which library to work on. It could be Keras, it could be Pytorch, it could be Mxnet. Since we are using Mxnet Gluon backend, I am importing Gluon prototype from Monk. Once it has been loaded, the next step is to create a project and an experiment. So this command will create a base directory named as workspace, and it will contain all your projects, and every project will contain all your multiple experiments. So we tend to keep it in a way that when we are working on a single data, we create one project for that data and multiple experiments on that data. Now every experiment contains a JSON file that will have the state of your experiment, or the project you may call it, like it has been trained or not, and if it has been trained, what the parameters have been used, how many models have been generated, which network was used, things like those. And an output directory which will contain logs and models. Logs are nothing but the status of your training, the accuracies that you got, the losses that occurred while training, and models contain all your output trained models. It could be intermediate files or the final one. So this will keeping the intermediate files helps to actually resume training if your collab engine breaks down. Now talking about the data. Let's download the data. I've already downloaded it, but you can run this command to download the data. So the data set has to be arranged in a manner where every subdirectory contains images of one type. Say all the images of cats, because this is cats and dogs classifier, all the images of cats in one folder, and that dogs in another folder. Another way of doing this is you put all your images in a single folder and a CSV file you create that points every image to its corresponding label. Either way, you can go ahead. And once that is done, you initiate the default parameter setup, and all the details will be printed accordingly. You can see every detail about the data set, about the dataset parameters that have been used, the shape, the batch size. These have been preset because it's a default mode. The transforms that have been used, the number of images that existed, which model was used, the optimizers, the schedulers, the loss functions, everything will be displayed here. Now, a small glimpse of what expert would do further on this is change the certain parameters. Here I have shown a very simple thing where I'm not saving any intermediate models. And post that you reload your experiment after making any updates, then you train it. Training takes place. The next step that comes is you want to validate your classifier as to how accurate it is. Validation data is never used for training. So you take up your project, you load your project with a small flag called as eval_info, where you are mentioning it to the Monk that it is being loaded in the evaluation phase and not for training. You load your data set, which contains images for dogs and cats and the corresponding labels, and you evaluate it. Once you evaluate, you get an accuracy of how good it is working on each class, as well as an average accuracy for the same. You can similarly use, you can similarly load the model in a eval or info mode to run inference on a single image. Like here, we have given it an image of cat. It predicts that 98% it could be a cat, and this one 91% it could be a dog. So if you train your classifier for more number of epochs, you will get better accuracy. So such things, if you train it for more number of epochs, or if you set your learning rate learning rate high or learning rate low, all these things can be experimented using Monk. And in the study roadmaps, you will get a general analysis of what needs to be done for, the best practices that needs to be followed. Now, this I have shown as a single experiment. Now, I would like to show you how you can compare multiple experiments. So in this notebook, it's a notebook from study roadmaps again. What we have done is we have trained multiple networks on data where it is being trained to diagnose a cell, a human cell is it infected with malaria or not? Now, we have created three networks. We have used three networks to train this classifier named as ResNet, DenseNet 121, and MobileNet version 3. So don't get confused with the network names. So once you go through our study roadmaps, you'll get to understand what these networks are. Now, we have done the training using the same method that was taken for the dogs and cats classifier, the default mode. And once that was done, we want to actually check which network works the best for us. So we load a comparison project, name it something, say sample comparison 1, and add all your experiments to it. Generate the statistics. You will get visual, all statistics will be displayed visually, where you can check the training accuracies, training losses, validation accuracies, validation losses, how long did each experiment take to train, what was the GPU usage time, which one actually worked the best for you. So here MobileNet V3 worked the best for us. So it gives you a very quick analysis of what can be done and how you can move with the next step. Comparing experiments is really important. A few other features of say Monk involve resuming a broken experiment. Now, say since a workspace folder is always created for you and your collab engine collapses, and say after 10 epochs, but you have to train it for next 100 epochs, you actually initiated it to run for 100 epochs, you can simply load back that experiment with a flag called resume_train, and it will run the entire, it will begin your experiment from the last point where it broke. So as you can see here, it skips the epoch from 1 to 10, and since the 11th one didn't complete, it starts from there. The next feature is to estimate the training time beforehand. So, I'm restricting things to Colab because most people tend to use that. If you are using an AWS machine, again, you would like to know how long your engine would be running to avoid unnecessary cost overhead on your company or as well as your say client. Now you estimate the training time, say for 100 epochs or 50 epochs, and you get an idea as to how long the system will be going to process the entire data set. After that, we have added a simple exploratory data analysis where you can check whether some images are missing or some data is corrupt, so that you can remove it before the training starts. Now, suppose the data is used, say like 800 GB or 900 GB, and one image out of it is corrupt. So it's the possibility of your training stopping at, say, the 90%, after it has completed 90% of a single epoch, it could stop there. So for that reason, you tend to remove all those corrupt images, as well as you can get a idea of class imbalance from here. After that, you can create your own custom network and visualize the same using Netron library. We have integrated the Netron library with our set, and it's very simple to create your own network from scratch. A typical issue people face with deep learning libraries is to create their own network, and because every next layer has to be specified how many features a previous layer outputs come in. It's so difficult for me to explain it here. It's even more difficult for people to actually understand and get it working. So we have created a very simple syntax where you can add your layers to a list, a nested list maybe, and it will create a branched network for you. You can visualize it on the go. No other library provides you this facility. And the last is I want to talk about is the hyperparameter analysis tool. Here we are taking up different learning rates and giving it to a single experiment to analyze and tell me which one works the best for me. On the basis of training accuracy, validation accuracy, training loss, and validation loss, I can compare each of these learning rates. All the parameters are kept same. Only one parameter is changing so that I can understand the effect of learning rate on my training. And for this one, learning rate as 0.1 isn't working, but 0.01 produces the least validation loss, so I'm going to go ahead with 0.01. Similar things can be done for different models. Now, there are n number of models to choose from. So, previous example, as I mentioned, there was ResNet 18, there was DenseNet, and there was MobileNet. Instead of creating 3 different experiments, I can take X% of data, say 5% of data, and run it for 10 epochs over all these models and check which one works the best for me. So this gives me an idea, a process, a structure to go ahead and work on my experiments and projects. So these are a few powerful features of Monk image classification library that you can definitely check up. And next I would like to hand over to Akash for a demo on object detection and Monk Studio, so that you get an idea of how an object detector can be created in similar structured manner. Thank you.
Thank you, Abhishek, for that in-depth hands-on tutorial. I hope it was enlightening to the audience. Next, what I'll do is I'll walk you through some of the overlapping patterns that we try to keep while standardizing workflow for different computer vision algorithms. So the development patterns that you just saw while building an image classification model, we try to keep the same workflow while building an object detection algorithm too, but with minor changes. So if you look at object detection research, every state-of-the-art research comes with its own set of dependencies and instructions to set up, train, and deploy. A majority chunk in prototyping is also spent in preparing a large labeled dataset and translating them into one format or the other. With MonkAI, what we try to do is we try to provide off-the-shelf, ready-to-use workflows with some of the state-of-the-art object detection researches. If you look at the model zoo, we provide with ready-to-use tutorials and trained models for multitudes of different application areas and signal domains. Let's take a look at how you go about building an object detector by using MonkAI. So the steps remain pretty much common. You start out by cloning the Monk object detection repository and setting up the dependencies based on which platform you're utilizing. Each of our tutorials usually come with its own set of knowledge base, the research papers or blog posts which could provide useful insights around the implementation that the notebook is built upon. Next, there is instruction around how to organize and prepare your dataset. For image classification, this was either foldered or CSV based. For object detection, it's usually training and validation folders along with a set of bounding box labels. Now, some of the popular formats that are used with object detection is usually Coco, Pascal VOC, or YOLO. With each of our example notebooks, we also provide ready-to-use scripts that help you convert from one popular format to another easily, so that you don't have to go through the hassle of writing those scripts yourself. To train an object detector, we begin by importing the detector functions and creating the detector object. We load the training dataset by passing the dataset path. Now, usually object detection training is compute intensive and requires a graphics card. Depending on the memory size of your graphics card, you can pass in the right batch size and set the number of workers. If you are using a validation set, you can pass the requisite paths to a validation set. Now, this notebook is based on training efficient detectors, which came out this year from Google. In the model name, you can pass which layer of the efficient detector you want to train. In the freeze head, you can set whether you want to train the backbone or you want to keep that frozen and just want to train the detector. In this case, the backbone is efficient network. Finally, you can set the right hyperparameters, which is the main game here. It's all about playing with the right set of hyperparameters and finding out which ones work the best for your use case. So We also have multiple available optimizers, loss functions, and so on. Finally, you can pass in the number of epochs you want to train your model for, the validation intervals, after how many epochs do you want to run the validation on your validation set, and the save interval, which is after how many epochs you want to save a trained model. Once you are through with your training process and have generated a trained model, you can infer using this trained model very easily. All you have to do is load the infer functions and create the infer object. You can load the model by passing the location of where your trained model is stored. And finally, using the predict function, which takes the image path and a threshold value, which is the confidence score, above which all bounding boxes are visualized. So each bounding box has an attached confidence score too, and you want to be mindful of this. And finally, you can visualize the generated outputs. So if you look at the overlapping patterns, there is a set dataset loading or preparation, the setting of hyperparameters, training of algorithm, and inferencing of algorithm, which is trying to wrap creating a computer vision application in a standardized workflow. Thank you everyone for taking some time out of your day and listening to us. I hope this keynote was useful for all of you. We are always on the lookout for researchers, developers, and programmers across the globe to try out our library and help us build an efficient and effective toolkit. We are open to contributors who would like to contribute to open source while honing their skill sets too. Feel free to reach out to us via any of our social media channels. Once again, I would like to extend my thanks to the organizers and to the audience members. Thanks a lot, guys.